Today, we're going to remind you of some information involving inverse trig functions, how to use them, what they find for us, and we're also going to begin getting into derivatives. So, before we do that, I'm going to remind you that inverses, or inverse functions, are functions whose x and y, or their domain and their range, switch with each other. So, if sine of y equals x, then the inverse sine of x equals y. Sine of pi over 2 equals 1. Then sine inverse of 1 equals pi over 2. When we're talking about a regular trig function, you plug in an angle, you get a trig value. When we're talking about the inverse, you plug in a trig value, and you get an angle. So it undoes what the trig function does. So for instance, cosine of pi over 4 is radical 2 over 2, which means the inverse cosine of radical 2 over 2 is pi over 4. Tangent of negative pi over 3 is equal to negative radical 3, which means the inverse tangent of negative radical 3 is equal to negative pi over 3. Before we can jump straight to domain and range of inverse sine, we're going to graph it. So if we talk about regular sine, we know that sine crosses through 0, 0 is at negative 1 and negative pi over 2, and is at 1 at pi over 2. So it looks something like this for our regular trig function. That's the red. Now our inverse is going to be the reverse of that. So instead of graphing negative pi over 2, negative 1, we're going to graph negative 1, negative pi over 2. 0, 0 will still be 0, 0. Pi over 2, 1 will now become 1 pi over 2. So the inverse of this function looks like the blue. Now the domain of that function would be negative 1 to 1 because that was the range of our sine function. And the range, we can't continue on with our sine graph beyond pi over 2 or negative pi over 2 because its inverse would not be a function. So we have to make the inverse stop at pi over 2. Which means when you take the inverse of some trig value, you must get an angle in quadrants 1 or 4. Your positive values are going to give you 1 in quadrant 1. Your negative values are going to give you 1 in quadrant 4. But remember, you must name negative angles if you're in quadrant 4, because from 0 to negative pi over 2 is quadrant 4, but those are negative angles. If you have questions on that, make sure you ask me about it tomorrow. Similar situation for cosine. We know that cosine starts at 0, 1, and crosses the x-axis at pi, gets to negative 1, or pi over 2, it gets to negative 1 at pi. Now we could continue on, but its inverse would not be a function. So this is all of the functions we need. If we switch these, 0, 1 would become 1, 0. Pi over 2, 0 would become 0 pi over 2. And pi negative 1 would become negative 1 pi. And it looks like it reflects over the line y equals x. Close. Y equals x isn't exactly right where it should be on this graph. But if we think about this, our range is, our domain is negative 1 to 1, and our range is 0 to pi. Well, 0 to pi includes quadrants 1 or 2. Positive trig values will give you an angle in angle 1 when we're doing inverse cosine, and negative trig values will give you an angle in quadrant 2. So quadrant 1 or quadrant 2. Tangent. If you think about the original original function, we have asymptotes at negative pi over 2 and pi over 2. Sorry about that. And I wrote pi over 4 and I meant pi over 2. And it looks something like this. If we would repeat any further than that, the inverse would not be a function. So let's talk about what that inverse is going to look like. We're going to have asymptotes at pi over 2 and negative pi over 2. This needs to look like a mirror image. So our inverse will look something like this, which means our domain is all real numbers, but our range is negative pi over 2 to pi over 2. Because our range is negative pi over 2 to pi over 2, our answers from an inverse trig function have to be in quadrant 1 or 4. And when they're in quadrant 4, they must be negative angles, because this portion of our graph is just to the left of the zero.
Excuse the interruption.
Because this section, this part I've labeled in green, is just to the left of the zero, and on our unit circle, clockwise past the zero or below the zero is quadrant 4, but those would have to be called negative angles. If you have questions on that, please ask me about them tomorrow or come see me sometime. So, let's try one. You've seen some new notation, this -1 and arc mean the same thing. So if you see sign to the -1 of x or arc sign, those are the same. I'm not sure why they came up with arc sign, possibly because they couldn't type that little -1, but I'm not sure. So, finding values from Pythagorean calculations. Tangent equals tangent of the arc sine of 1/3. Well, I can't think from the pie plate of an angle that has an arc sine of 1/3, so I'm simply going to call that theta. And I'm going to make up an angle whose sine value is 1/3. So if I call that theta in my picture, if its sine value is 1/3, I know that this is 1 and this is 3. And no, my triangle is not drawn to scale. That's okay. Knowing that, I know that this side, this unknown side, I'll call x, that x squared plus 1 squared equals 3 squared. Which means that x squared equals 8, so x equals plus or minus radical 8, or 2 radical 2. Or radical 8, or 2 radical 2. So x is 2 radical 2. Has to be positive or it would be a side length. So now that I know every possible thing about this angle, all sides of the triangle, I can tell you what tangent of theta is. Well, tangent of theta is opposite over adjacent, so this is going to equal 1 divided by 2 radical 2. And if you needed to rationalize it for a multiple choice answer, please do. Similar idea here. I know tangent goes up to 2, but I don't know an angle whose tangent is 2. So I'm going to call this angle theta. And I'm going to draw a picture of theta. They tell us the tangent's 2. Well, 2 is a fraction, is 2 over 1. So that means their opposite must be 2 and our adjacent must be 1, because tangent is opposite over adjacent. Which means our third side, using the Pythagorean theorem, should be equal to 5, which means x is radical 5. So what's cosine of theta? Well, cosine is opposite over hypotenuse. Sorry, adjacent over hypotenuse, I apologize. So this is going to equal 1 over radical 5. Let's try a couple more. This next example says cosine, inverse cosine of pi over 12. All right. We don't necessarily know the cosine of pi over 12, but if you look at this closely, inverse cosine and cosine are somewhat going to cancel each other out. So when you run into a situation like this, where inverse cosine and cosine cancel each other out, you just have to make sure that that pi over 12 is in the correct quadrants. If you remember back from the previous page, cosine angles must come from quadrant 1 or quadrant 2. Pi over may or may not be in the correct quadrants. If you think back to the previous page, inverse sine must give us answers in quadrant 1 or 4. Well, 2 pi over 3 is in quadrant 2. So my gut would say 2 pi over 3, but it's not going to work because it's not in the correct quadrants. What angle in the correct quadrants, that would be 4 or 1, has the same sine value as 2 pi over 3? Well, inverse sine of radical 3 over 2, because 2 pi over 3 sine value is radical 3 over 2. If we think about it in the correct quadrants, we find out that the angle that makes this happy is pi over 3. Now, derivatives of inverse, or I'm going to show you a proof. Y equals the inverse sine of x, then its inverse is x equals sine of y. So, if x equals sine of y, if I derive derivative of x is 1, we're deriving in terms of x, derivative of sine of y is cosine of y dy dx, which means dy dx is equal to 1 over the cosine of y. And let's talk about the angle for a second. I know that x equals the sine of this angle y, right? Because of what they tell us right here. Well, x is a fraction, x over 1. And sine is opposite over hypotenuse. So I know that this is x, that this is 1. I also know that this missing side is going to equal the square root of 1 minus x squared. 1 squared minus x squared, so this is going to be radical 1 minus x squared. So cosine of y is radical 1 minus x squared. So our derivative, dy dx, is equal 1 over cosine of y from our picture is radical 1 minus x squared. What that does is help to prove that the derivative of inverse sine is r 1 over x squared. The other two I'm not going to go into the proof for right now, but you should memorize all of these. Inverse cosine has the negative out front, but it's just like inverse sine. And the derivative of inverse tangent is 1 over 1 plus x squared. So, now that you've seen the rules, let's try some. Derivative y equals inverse cosine of x squared. We're going to derive. So y prime. If you look at that table or the box just above, we know that the derivative of cosine of inverse cosine is negative 1 over 1 radical, negative 1 over radical 1 minus x squared. And that's when we have an x in our inverse cosine. We don't have an x in our inverse cosine. We have an x squared. So we need to put an x squared, and then by chain rule, we need to multiply by its derivative of 2x. So our inverse is really negative 2x over the square root of 1 minus x to the 4th. Let's try another one. Sine. Its derivative is 1 over radical 1 minus something squared. Now that something is whatever's in our inverse sine function. So I have to put my radical 2t, but then I have to multiply by radical 2t's derivative, which is radical 2. And I find out that my y prime is radical 2 over the square root of 1 minus 2t squared. Finally, we have a tangent. We actually have the product rule going on here because we have a product. So we do the first. Derivative of the second is 1 over 1 plus whatever's in our tangent, inverse tangent function squared, plus our second times the derivative of the first. If I simplify this a little bit, you'll find that your derivative is b over 1 plus b squared look these over, check them out closely. It's not the easiest thing in the world, but for today it shouldn't be too bad. Anti-derived them. The substitution is a little bit trickier, but we'll save that for another day.